Method 2 class. I hope you spend a very blessed and wonderful weekend. Welcome, Simeon, Kashupi, Ushongo, Abraham. The class representative is just joining us now. She's late. So without any further ado, I will quickly share the screen with you and we'll go through what we covered last time. Just a brief recall. Okay, so last time we talked about economized power series, but before that, we stated this Chebyshev approximation theorem, where we are trying to fit a polynomial expanded as a linear combination of the basis. The Chebyshev approximation, meaning that the basis is formed by the Chebyshev polynomials. So if we take the n plus 1 root of, because here you can see that we have a total of n plus 1. So if you look at t sub n plus 1, this is a Chebyshev polynomial of degree n plus 1, capital N plus 1, right? So if you take this Chebyshev polynomial, it has exactly n plus 1 roots. And those x plus 1 roots are the point or considered to be our data point, right? So we take that to be our set of data points. So we take those points and we try to fit our function or this function approximation of f. We try to fit it to those points. And as you can see, the function we are trying to fit, the x component will be the roots of this Tn plus 1, the Chebyshev polynomial of degree n plus 1. And the data point will be f of this x, that is the value that this f takes at those points. So that will be the set of data points. So we take this, we fit at that, and we know that it's a least square problem. So the least square problem, what we need to do is to determine the coefficient Ck. And we know already that through the least square method, since the Chebyshev polynomial form an orthogonal basis, and we know that the non-zeros, when m is equal to n, equal to 0, will be n plus 1 by 2, and when n is equal to m equal to 0, there will be n plus 1. As you can see here, n plus 1, and the other one will be n plus 1 by 2. Okay, so we use that fact to solve for the CKs or the CJs or whatsoever through this orthogonality. This is the orthogonality property that I asked you to prove, and you have till the 17th. Oh, I even forgot. I remember that I promised that I will post the information about the lemma that we'll be using to apply this to, and nobody reminded me about it. So I need to write it somewhere so that after the class, lemma. All right. So we saw that if this is orthogonal, we can easily find the coefficient, right? So And the coefficients are given by this. C0, Cj, where j runs from 1 to n. And we tackle this problem as an application. The problem is to fit, to approximate the exponential x over the interval -1, 1. So the data point there will be the roots of. So this is our capital N, and we know that if n is equal to 1, the number of roots will be n plus 1, right? So we have a total of 4 roots. N plus 1, that is 3 plus 1 is 4. So the Chebyshev polynomial, that will be, whose root will be computed, will be Chebyshev polynomial of degree 4. And these are the root of the Chebyshev polynomial of degree 4. You can see that there are 1, 2, 3, 4 roots in total. So you use these 4 roots and substitute into the formula, so you get these various values. And for the economized power series, we say that the purpose is to use a series or a truncated series and try to minimize this. That is to reduce the number of terms, but we still require the approximation to be of the same order. So that's what we apply here for the economized power series. And I ask you to, okay, we compare, we saw that, as you can see for yourself, it's not a secret for anybody. You can see through this result that the economized power series gives us a very good approximation. With less term, you can still have a good approximation compared to the Maclaurin, because Maclaurin will still have more terms. Okay, so today what we are going to do, we are going to introduce the concept of Chebyshev series. Chebyshev series. Of course, to that there are 2 approaches, and we are going to tackle the easier approach. Right. Okay, the more complicated approach, I think we'll do that through a tutorial. Let me check first. I don't know if in tutorial 1 there's something similar. I want to check if I gave you something that relates to that. Oh no, unfortunately it's not there. Yeah, I find the series, but the one that I'm asking here in tutorial 1, exercise 3 what? 3.4, exercise 3.4. If you go to Chebyshev polynomial and series, exercise 3, and then you go to number 3. Exercise 3, question 3. No, question 4. Exercise 3.4. Okay, there's a question about the Chebyshev series there, but the Chebyshev series as asked in this question is the easiest, right? It's not the more complicated one. Okay, so let us tackle that one first. Let's tackle that one first. But the more complicated one, you don't need to approximate the way we are doing here. So it's similar to Fourier series. So that's why maybe it's after we cover the Fourier series that we might come back to that one. Because it's through the Fourier series that you'll be really able to do that. The Fourier series. Yeah. Okay. So we know already what is a series, a normal series. When you express a series as a power function, right? So you can see that the basis of the series here is x to the k. You can see here. This is like a power function. You have a power function, and then you take n to the infinity, gives you a series. And this power function is about 0. So you can see that if you are on the interval -1, 1, you are in the neighborhood of 0. So x0 here is 0. So that x0 is 0. Right? In the neighborhood of 0, 1, -1, 1. That is we are in the neighborhood of 0. So x0 in this case is 0. So that's how you expand. So the easiest way from Maclaurin series, the easiest way to obtain a Chebyshev series is just to re-express your xk in terms of t1 up to tk. Right. You can always do that. If you have from t0 up to tk, you can combine them and extract xk, which in fact appears in tk. Yeah? If you write tk is a polynomial of degree k. So being a polynomial of degree k, this xk will appear. So if you can write that as a linear combination of t1 up to tk, you can see with me that it's easy to take this x to the k and substitute in this formula, and therefore you obtain a polynomial in this form. And you can see now that the basis will be a Chebyshev polynomial instead of a power function, as you can see here, can't be complete. So this is what we'll call a Chebyshev series. So let us look at a few examples. Obviously, what I want to say here is that this can only be accurate if you are approximating polynomials. I mean, you want to expand polynomials, right? This formula, as I explained, will be accurate. It will be exact. Otherwise, it will be just an approximation. It will not be accurate. Why? Because, let's say, for instance, in this case, you can see that this is a power series, right? And I say here that you take xk, but see that xk go to infinity, and you cannot do that up to infinity. Because in order for you to write this x to the k, you see that you need everything up to tk. Now, what if, for instance, your power series, it goes maybe to, let's say, even 20 only. Let's go to 20. Then you have to compute this up to 20 to extract this and to substitute everything. So you see that it is really tedious, right? It's really tedious to do as a computation when you use this approach. It's really tedious. But if you have a lower order polynomial and you want to perform this substitution, it becomes easy. You can do that. You can easily do that. But what if you have a series that you really want to substitute and get all the terms? This approach will not work. It will not. But the second approach, which you might be required to do that in an assignment, or still, if I don't forget, we might organize a tutorial session where I'll try to go through and explain to you how to do that. It's similar to Fourier series, but we first need to cover Fourier series before we can come back to the case where you have an actual series where you want to perform this substitution. Okay, so let's look at this example. You can see that if you want to expand exponential x in terms of Fourier series, what we are going to do, actually, we are supposed to get all the xk up to infinity, but we cannot do that. Here, we will just use a few of them. See here, for instance, we computed up to x6. But don't forget that if I use x7 will have terms in T0, T1, T2, up to T7. You see that in that T7, C6 will appear. I mean, in X7, all these T will appear also. You see, meaning that there is a component in T0, T1, T2, T3, T4, T5 that will be in X to the 7 that I will not substitute if I use only these terms. So if I use a few, that is a finite number, and try to substitute in a series, their contribution that will be missing. And therefore, my approximation would be, I don't know whether I would say a poor approximation. It will be an approximation which will not be an exact approximation. I cannot actually say how accurate it will be. Okay, let's look at this example and substitute. You will understand what I'm talking about. Okay, so here we have our xk from k equal to 0 up to k equal to 6. That's what we have here. So we take this, we substitute into this expression of exponential. Right? You see that we substitute up to x6. We don't have x7 here. As I explained earlier on, in x7 you have some of these components which are supposed to come and add up to these ones to give us a more accurate result, but they are not present. So at the end of the day, what I obtain here is an approximation which is not that good, but it's an approximation anyway. But if this were a polynomial, because for a polynomial, you have an exact finite number of terms instead of an expansion or a series. So if you are given a polynomial, you can use all the xk's present in the polynomial and substitute. The approximation that you obtain will be exact. That approximation will be exact because it's no longer a series that you truncate and substitute, but it will be all the terms that will be substituted. I hope it's clear for everyone. If there's any question at this stage, you are allowed to ask before I proceed. Any question, any concern? Okay. So if no question, so it means that so far so good, I can proceed. So you can see that in this expression, this one is substituted by that. This x is substituted by t1. 1/2 into x squared is substituted by this one, and so forth. Now, so we substitute all those terms and we group the terms together, the like terms. You see that this is what we substituted. You see, we substituted all these terms. All these terms. Right? And at the end of the day, we group. You can see that T0 is present here, and it's also here, and it's here, it is here. And it might also, it will necessarily appear in other terms, you see, in these dots. But we are not considering those terms. We only add up terms in T0 that are present, and you see that this is what we have. But there are other terms in T0 that are not added to this one. So that's what I was saying, that this will just be an approximation, right? It will not be exact. Okay, I hope it's clear. So you do the same thing for T1, T2, T3, you put them together, and then you get something of this form. So this is our series, right? In in T, our Fourier, I mean, our Chebyshev series. This will be our Chebyshev series. Woo! Finally, wow! Fourier series, wow, wow! Some people's hearts are already beating. Ooh, Fourier! Some people want to see Fourier. Some are happy, of course, like me, I'm happy. But some other people, ooh, they are panicking, ooh, they are shivering. I'm not saying that it's you, but you know yourself in your heart that is you. But it's not you. It's not you, 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 but it's you. Anyway. All right, all right, all right, all right. This is a very nice topic. I like it. It's sweet. It is sweet like what? Like cake. Damara cake? Yeah, maybe Damara cake. Damara cake. Okay. Ooh, there are some people that don't like integral. You have to like it. Integrals are nice. They are sweet. They are wonderful. They are maravilloso. Okay. What is a periodic function? A periodic function is a function that repeats itself after a certain interval, after a certain time interval or space interval, because you have periodicity in time, also have periodicity in space. Periodicity in time, what? Okay, like seasons are periodic in time. Today is the 9th, no, sorry, the 8th, the 9th is my birthday. Oh, I even say it. Okay, so today is the 6th of September. But last year there was also a 6th of September, right? That's periodicity. After a year, this time period will repeat. So you can see that's periodicity in time. You also have periodicity in space. Periodicity in space. Which example can I take? Yes, periodicity in space. Ooh, like maybe the sine function. Obviously, if you write the sine function with your variable to be the space variable, you see. Okay, you can even see it. Yeah? If you use even in space, if you use a wheel or the trigonometric circle, remember the trigonometric circle. Or if you take a wheel, you turn around the wheel. You take maybe a point and you turn it like this. You can see that you can start from this point. You turn your wheel, it will go, and then you come back to this position. You see, that's periodicity in space. You turn, you come back to that position, you turn, come back to that position, you turn, come back. And you can even represent that also when you move, you go somewhere, you come back to the same position or to the initial position. That's still periodicity in space. You see, you move, you can go to town, you can travel, you go, and then you come back to a given position. So there are many ways to see periodicity. So periodicity is all over around us. Periodicity in time and in space. Okay, now mathematically, this is how we define a periodic function. So a function f is periodic and of period p, capital P, you can see here, if f of x plus p is equal to f of x for any x. So you can see that, let's say for instance, okay, the case of the cosine function is obvious, right? Cosine function, you know, I don't know if you all know, but I know that, or some of you know that, if you take a cosine function, let's say we know that cosine of 0 is 1, right? Cosine of 0 is 1. Now, if you move along the trigonometric circle, you move around, you make a complete cycle, which is 2 pi, that is or 360 degrees from that position. You turn around after 360 degrees, which is 2 pi radian, we come back to that position. But now, in terms of angle, the new angle there will be 2 pi. It will no longer be 0. But the value of the cosine of 2 pi will still be 1. Now, if you turn again, the new position, the angle will be 4 pi. And the cosine will still be the same, 1. After another circle, complete cycle, the new value of the angle will be 6 pi, and the value will still be 1. So you can see the cosine x is a periodic function of period 2 pi, meaning that after 2 pi, I come back to the same value or to the same position, which gives us for the function the same value. Then a complete circle, cosine will give us exactly the same value. Even though the angle is different. Initially, I was here. After a complete cycle, I come back to that position. So I travel a certain distance around the circle. I still come to that position. So the function, which is cosine, the sine function, is periodic, and the period is 2 pi. This is a simple case, simple example. Now, what was the purpose of this graph? Anyway, I think I'll come back to that. Now, let us define what is a Fourier series. In this class, we will assume that the function we are dealing with are periodic and of period 2 pi. Even though this is not a must, you can still define the same notion of Fourier series for a function of a particular period. The period can be 1, it can be 2, it can be anything, but for us, we are fixing 2 pi. Through a change of variable, you can always bring it to a function of an arbitrary period, capital T, which can be any number, and therefore, all this formula will be readjusted. But in order to avoid complication with an arbitrary series, or I mean, with an arbitrary period, we fix it to be 2 pi. Why? Because a common function like sine, cosine are 2 pi periodic, right? That's why we fix it to 2 pi, to make things simpler for you. And obviously, for those of you who are interested, you can use, there are many textbooks in the library available online. There are many tutorials where you can, where you get the definition of Fourier series of a particular period, an arbitrary period T. You are given formula with that. Okay, so if you are really interested, I can still give you a sheet with those formulas where we define Fourier series of a period where the function f is of period t. Then in that formula, if the period of your function is 2, 1, 1/2, you can just go inside and substitute. If you're interested, I can do that. Otherwise, stick to this for the time being. Okay. Now, we are going to define the Fourier series. Our Fourier series is denoted by S sub f. Obviously, in the note, there's no sub f, but I added the sub f here to make life easy, or to make things easy. For you to understand that the function that you are expanding in Fourier, in terms of Fourier series, is the function f. Of course, it looks like a cross, but it is f. It is f. This one. Okay, so our function f is periodic, of period 2 pi, and is also piecewise continuous on the interval negative pi pi. Okay, now I will explain what it means. And if you look at this graph, if you look at this graph, I was trying to explain what it means to be piecewise continuous on the interval negative pi pi. Okay, now if you look at the graph, this one, this is our interval negative pi pi. This is the interval, this one. This is, oh, anyway. Okay, you can see this. So this is negative pi and this is pi. So you can see that in the interval negative pi pi, we have a function here which is continuous. You see? It's only continuous where in this interval negative pi pi is continuous there. But it's not continuous throughout the real line. Only in the interval from negative pi to pi, I can draw my function from negative pi to pi without lifting the pen. See, that is piecewise continuous, meaning that it is continuous in that subinterval. Now, piecewise continuous will mean that I can shift by periodicity, because when it says periodic, it means that this value will repeat after 2 pi. So in order to do that, I can shift it by 2 pi to the left and to the right. So if we shift this graph, it means that I copy that, shift this interval by 2 pi. Okay, you see that this one, this is pi, right? If I shift it to the left by 2 pi, it means that I'm shifting to the negative directions, right? I will be adding negative 2 pi to this and negative 2 pi to that. Right. So if I add negative 2 pi to pi, it gives me negative pi. So you can see that this value here, when I will shift, will become this one. And the value here at negative pi, if I shift by 2 pi, negative pi minus 2 pi gives negative 3 pi. So this value here at negative pi will be repeated here at negative 3 pi. So I can shift like that till negative infinity. And to the right, I do the same thing. So you see, that is my periodic function. And you can see that it's piecewise continuous because it's discontinuous here, discontinuous here, discontinuous there, discontinuous here, discontinuous there. So that's what we call piecewise continuous. You first draw your function in the interval where it is defined from negative pi to pi, and then you shift to the left and to the right by 2 pi, because we said that it's 2 pi periodic. Then you get the full picture of the function. Okay, so now this is how we define our periodic function. Our Fourier series. This is how it is defined. So the first term is A0 by 2 plus, now here you have a series. Summation k running from 1 to infinity, ak cosine kx plus bk sine kx. So this is our Fourier series. You see? This is the Fourier series. Okay. Here you see f does not appear explicitly here in the formula, but it will appear in your A0, A, K, and BK. So the function f you are trying to expand in terms of Fourier series will appear here. So these AKs, BKs depend on f. And how do you derive the formula for AK and BK? They are obtained through what we call Euler's formula. And the Euler formula for AK is given by this formula, and for BK is given by this other formula. Okay, now if you look at the formula, what do you realize? So you can see that AK, if you look at the factor of AK here in formula 138, this box formula, you can see that AK is the factor of cosine. So similarly, AK will also depend on the same cosine. So that's why in this expression, you can see that AK is an integral of the function f of x that we're expanding into what? This same cosine, whose k is factor of in the expansion. And similarly, you can see that in the Euler's formula, bk will be the integral of f of x and sine kx. That's what you have here. So that's the first thing you have to bear in mind, to always remember the formula, not to memorize, to remember, because you develop tricks to remember, okay, if I want to write the formula, how is it going to be, right? So AK cosine, BK cosine. So this AK, when I will expand, when I will write the formula for AK, it will be an integral of the function f times the same AK, I mean cosine. And for BK, it will be f of x times this same sine kx. Okay, now the next thing, the other thing you need to know is about this factor and the limit of integration. For the limit of integration, there's no problem, because our function is defined where? In the interval negative pi pi. So it's obvious that you also get the same interval here. The limit of integration will also be negative pi pi, negative pi pi. But here, this is 1 by pi, 1 by pi. One by pi, 1 by pi. So that is the factor. Now, in terms of the range of k, here in the expansion of the Fourier series, A0 is isolated, right? You can see here, A0 is isolated. So, so your k will run from 0 to infinity. So you take all the values, including this A0. But for bk, you can see that in our series here, k starts from 1 to infinity. So your bk is not defined for 0, as you can see. Bk, the bk's only are defined from k running from 1 to infinity, whereas for a case, you have a0 here and you have a1, a2 up to a infinity. So in this formula, k will take all the values starting from 0, whereas for bk, k will only start from 1. So bk is not defined for k equal to 0. It is not. Never try to compute, never attempt to compute b0. It does not exist. You can see from the formula. A0 exists, A1 and up to infinity. But for B1, B0 does not exist. It starts only from 1 to infinity. So this formula is only true for K equals 0, 1, 2, up to infinity. But for BK, K starts from 1. So these remarks are very important for you to remember, not to memorize, but to remember. Okay. The first exercise, as you can see here, we know what is an orthogonality property, right? We know already what that means. So now we are asked to show that sine and cosine, sine function and the cosine function are all, they are orthogonal. And you are actually given explicitly what you have to prove. These are the orthogonality properties here, right? For integers m and n, because if you look at the expansion here, you can see that we expand in terms of cosine kx, where k takes the value 1, 2, 3, 4, 5, of course, starting from 0, 3, 4, 5. So all the integers are here, positive integers, of course. Similarly for that. So in order to compute these coefficients, like in the Chebyshev case, remember when we wrote an expansion of this form, we needed an orthogonality property for the element of the basis, right? So that is something similar we want here. But since our point, the x are not discrete, x are actually continuous on the interval negative pi pi, they are continuous. It takes all the values in the interval, so they are continuous. Therefore, our orthogonality property will be in terms of integral, not in terms of summation. Summation is when you have finite set of data points, but integral is when we have continuous data point. So this is the orthogonality property that we are given here. For the sine function, the integral from negative pi to pi, because that's the limit of our integration here, negative pi pi. So if you use that interval negative pi pi, sine n x is always 0, but for cosine, it will be 0 when n is not 0, but when n is 0, it will be non-zero, because we know already that when n is 0, cosine 0 is 1. So if you substitute n equal to 0 here, you agree with me that you have 2 pi, right? From this integral, it will give you 2 pi. Okay. And for this one, it's obvious because you know that you can always write cosine, the antiderivative of sine. What is it? It is negative cosine nx by n. You agree with me? That's the antiderivative. And you know that if you integrate cosine, the values of cosine, because we already have the n there, you integrate cosine. You don't even need to integrate. It's even easy to see it. You can even see directly from the graph. If I sketch a graph here, you even see it's easy to show that directly. This interval is centered at 0, right? You can see that. This is centered at 0. Now, if you take this, we know that the sine function is an odd function. So sine function will be something like this. So we have 0 here. You can see that there's a symmetry about 0. So if this is pi and this is negative pi here, you can see that this value is positive and this will be negative, but the same, right? The opposite. So if you add them all, give you 0 automatically. You can see it. That's why you need to understand this graph and trigonometry, right? This thing will really become easy for you. So by symmetry, it's just by symmetry about the origin. So they will just cancel out. And if you integrate directly, you still see that it will cancel out directly. Okay, so that is it for this one. Now for this one, you use trigonometric formula. You can write this as a sum. You can write this factor as a sum. Similarly, all these are sums, and then you integrate. It will give you 0 for this one, and for that one, it will give you 0 when n is not n, and when n is equal to m, it will give you pi. When m is equal to m, for instance, in this case, it will give you sine square nx, which we can write in terms of double angle, right? You can write that as cosine or sine of double angle, and you can easily integrate to get this value. Similarly for this one, double angle, when m is equal to n. But when they're very different, so you can really prove this. You can really prove this one. You can prove it yourself. And now you can use this result into this expansion and solve for AK, BK. You can do that. How do you do it? Obviously, to do that, you first assume that this series will converge towards F, right? You assume that this series converges, and it converges towards F in such a way that you can substitute this S with F. So if you write F equal to that, then you multiply. You see what you have here. You have F of X here, then you multiply by cosine, maybe K prime X or cosine N X, and then you integrate both on both sides, and you use one of these formulas, which is this is our orthogonality property. So you use this orthogonality property to solve for your AK and for BK, right? So when you multiply F of X by cosine X, you multiply throughout. Also here you have cosine whatsoever cosine here. You see that when you integrate the sine and the cosine, sine and cosine, you see that this integral will always give you 0. Sine and cosine will always give you 0. So this will give 0. And what you get will be only in terms of AK, because there will be cosine here. So we have cosine something there. Right. So cosine, you are here. Cosine. So there are cases where there will be 0 when they are different. And there is only one case when it will be non-zero, when m is equal to n. And you can see that in this summation, all the other terms in the sum will give you 0 here, but only one term will give you non-zero. And that is the AK that you will extract and divide by the corresponding pi to get this formula. You can see that the factor here is pi, and that's exactly the pi that you have here, because that's the cosine. To give you that. Similarly, when you do the same thing, multiply by sine, cosine sine for BK will cancel out, and then for AK will cancel out. Now for BK, you have sine. All the other terms in the summation will be 0 except 1 when m will be equal to, or when the two integers there will be equal. And the factor will be pi, and you will divide by that pi to get this denominator. So you see that it's easy, yeah? You just use this trigonometric property in this expansion where the S is replaced with F, and then you use the orthogonality property, integrate, and that is it. You can get your AK and BKs. So please write that. Take a piece of paper and write that property. Make sure that you understand all the steps, because that's how you'll be learning. Good. Now, we are going to state our first theorem. That is Fourier expansion. Here in the definition of Fourier series, you can see that we are using S sub f of x to define the series. Meaning that in the series, this series might diverge. This can go to infinity. When you define the Fourier series, you just define the series. Be that the series converges or not, you just write SFX equal. That is the formula for your Fourier series. Now, in this theorem, for the Fourier expansion, the theorem gives us a necessary and sufficient condition. Let's say necessary condition for our series to converge, because now we are dealing with the convergence of the series. That's why I termed it by Fourier expansion. Right. So you have results. You have result, convergence, result in this case. So let us look at the assumption for convergence. So S sub f of x is a Fourier series of this over the interval. Oh, it's negative pi, negative pi, not pi negative pi, it's negative pi. Please change that. Negative pi. Okay, so now if the derivative, the first derivative of f is piecewise continuous on the same interval negative pi, and has left and right hand derivative at each point of the interval, then the Fourier series will converge for all x in the interval negative pi. And it will converge towards what? It will converge towards f of x. So now you can see that f of x and s of x will be equal. And it gives us what we call the Fourier expansion of the function f of x. So that's the convergence. So it will converge to f of x when this condition is true. So you see the condition here is about f prime. F prime. Originally, we know that f itself is piecewise continuous on the interval negative pi. It is piecewise continuous and of period 2pi. That's the information we know about f. Now, we need an extra information on the first derivative of f for the convergence of the Fourier series S of f of x. So this will converge when f prime is also piecewise continuous, like f. But there's an extra condition that f prime has a left and right derivative at each point of the interval, negative pi. F prime has left and right derivative. If that's the case, the series will converge to f of x. But now what if, of course, there's this discontinuous point, because if you remember from this graph, we saw that these points are point of discontinuity. And the point of discontinuity, as you can see here, are all odd factors of pi. Odd factors of pi, like 1 pi, 3 pi, 5 pi, 7 pi, and then they're negative right there. Those are point of discontinuity. So at discontinuous point here, the point of discontinuity, we call them A. The Fourier series will converge towards what? The sum of f a negative plus f a positive by 2. Of course, f a minus and f a plus are the left and right hand limit. Left and right hand limit. What does that mean? It means, I will write it here, that a, okay, I will write here plus or minus, or I can start with minus, and it doesn't matter. Is equal to the limit of f of x, if you want, when x tends to a. Okay, for the negative is, I would say, oh no. Okay, for the negative here, I would say the limit will be this. It tends to A from the left. You see, from the left. And now for positive, it would tend to A from the right. What does that mean? From the left means that if this is A, I have the function here and this is A. So when the limit, you come from here, like this, that is from the right, which is the second case. When I say tends with greater sign, it's when you come from the right, like this. Now, when x tends to A from the left, well, it's less, it's when you come like this. So this is the left limit, this is the right limit. And that's what we have here. Okay. Okay, so that's for the theorem. There is an example here, but we will not do it today because it's already time. Please, I encourage you to read because we'll come back to this tomorrow afternoon, to this example. Please read through and make sure that you understand all that we covered up to here and prepare for tomorrow by reading what is done here so that I would just go straight to the explanations. Okay, I think we'll stop here for today. Thank you for your kind attention. God bless you and see you tomorrow. Bye-bye.